Let's start today's topic, okay? Now, reinforcement learning algorithms are classified into two main classes. There are different ways of classifying RL algorithms, obviously, but one classification is based on the requirements of the model, okay? Model-based reinforcement learning, or MBRL, and model-free reinforcement learning, as in MFRL, okay? In this course, we will be focusing only on MFRL primarily and entirely, in fact. This class, MBRL, in fact, this lecture presentation will not be very long, so hopefully we'll complete it within, say, half the class time, because this is just to give you an understanding of another paradigm of reinforcement learning called MBRL, okay? This doesn't have to do with our control application, so that's why I'll not be going in detail in this topic, all right? So it will be very quickly just an overview of the different algorithms that you have, what MBRL is, why is it different from MFRL, okay? So from the name, you understand that there is a model involved here, okay? Okay, before that, let me get a few things clear, okay? Now, most of you are working on projects, right? So you are trying to develop an agent that is a controller for a system, right? When you are doing that, you're using either MATLAB or Python or C++, some kind of programming language, right? In which you are developing your model or system plant, right? You have your system there. And you are using algorithms like maybe DDPG or SAC, PPO, some of these algorithms. All these algorithms that you're using are model-free algorithms. They are not model-based, okay? However, now you must be thinking that, okay, there's a contradiction. We have a model that we have in the simulation, but we are using an algorithm. How are they model-free? It's a natural question to arise. So here comes the difference. When you have a model in simulation, it is basically something which you are providing the RL agent, the RL algorithm, to learn a policy on, okay? The RL algorithm will not care about how that actions convert into the outputs that you're getting, okay? I'll try to explain it with an example, okay? You get into a new house, okay? There are doors in that house, okay, which has knobs, okay? Now you know this knob, you hold it with a certain force and rotate it with a certain torque, and you know the door will open, okay? But you go into a new house, that house have slightly different or maybe harder or softer doors, okay? So you don't have to apply as much torque in that, or probably more torque in that, okay? You do that again and again. You do that, say, probably 10, 15 times, and then by that time you realize that, okay, fine, this is the force I have to apply, this is the torque I have to apply to open this door, right? In this case, do you actually understand, or do you try to even understand the physics of the lock, like the mechanism of the inside the door? No, you don't. All you're trying to map here is how much force you must apply, or how much torque you have to apply to open the door without breaking the lock, okay? Assume the lock is very fragile, and if you apply more torque than that is required, it will break, right? So what are you doing? You repeatedly do it by trial and error. You learn a given policy in your head, right? And that policy is hold it at this much strength or this much force, and then rotate it with this much torque, which will open the door, okay? Now assume that the lock is very expensive, or the door is very, very expensive, okay? And every try you do, it will break the lock, maybe, if you don't open it correctly. Okay? In this case, what you do is, you're like, okay, fine, I will make a simulation of this, okay, a virtual model of this, and I will try practicing on that model, okay? But you don't know how to make a model, okay? So you go to a person X, you request that person, can you please make me a model of this door so that I can practice, and before I get into that new house or new building, I know exactly how much torque and force to apply to open that door. You go to that person X opens the door, models that thing for you, and gives you that model. You have some kind of virtual interface between that model and you try practicing that. You learned it eventually. And then you go to the door in real world, and then you open it in first attempt, okay? No locks broken, no doors broken, no loss, right? The door opens. You know exactly how it is. Do you now, in this case, know how that model is or what that model is that the person X gave you? You don't need to, right? But there is a model. But do you know anything about that model? Did you need to learn about that model to develop the correct intuition of opening the door? No. That is model-free reinforcement learning, right? In reality, in an ideal world, say you have a drone. Okay, again, we'll stick to the drone example. Say you have a drone, okay, and you want to fly it to a given altitude, okay, but you don't know anything about the drone, as in how much torque would be required to lift it up, or sorry, how much thrust would be required to lift it up, or what would be the remote control toggles, nothing, you don't know anything about it, okay. Now imagine trying this on the real platform, and drones aren't very cheap, they are expensive. You would end up breaking many drones before you learn it. So which is not very feasible and efficient. So what you do in that case is you create a virtual replica of that drone that you have and you do the training on that virtual replica. Okay? You don't care about the physics. Okay? If you model it good, if you get it from somewhere, that's good. You don't need to know the equations. Get it? As opposed to classical controllers, like say MPC or LQR. Okay? These are classical control methods for which you need to have the state space model or the transfer function model in order to get you can develop a control law, but for the gains of the controller, you need to have, say, LQR, the state space model or the transfer function model, or some of the system models, the equations as in. Right? This is different in model-free reinforcement learning. You don't need this. Clear? So now you understand what model-free here is. It doesn't mean that you do not need any model and you can directly learn out of nowhere and then apply it on that system. No. It simply means that you don't need to understand the dynamics of the system in the sense of the equations, right? And this gets particularly useful in scenarios where the system model is very complicated or there are a lot of uncertainties in the system model. In the sense of, say, in the case of drone, okay? We model drones, you must have come across, or for that matter, any system, the mass spring damper system, or any other mechanical system that you might have seen. I'm sticking to example of mechanical system here because of the course, controls. So you must have seen that you model it, okay? Like the mass spring damper system, very basic system. You have mx double dot plus kx dot, sorry, bx dot plus kx is equal to f, whatever your input force is, right? Here, you need to know this exact equation first, okay? Plus, you assume that there are a lot of things that are physically present in the system, but you simply ignore them, right? So there is a lot of uncertainty in even such a simple system that you ignore for the sake of developing the controller for that system, right? However, with reinforcement learning, because you don't need this equation, you can add some sort of uncertainty through noises or maybe Gaussian processes. That way, you will end up with a model which is more adaptable, and if you train your RL agent on that models, it will be more adaptable even to changing conditions. Got it? Plus, you must have, I told earlier as well, that for classical control methods, you more often than not require a linear model of the system or the plant that you're using, right? However, in reinforcement learning, there's no such requirement. Also, another thing is when you develop the cost function for classical control methods, it must be differentiable, it must be continuous. So therefore, there are some requirements that the cost function must obey. However, in reinforcement learning, reward function is the analogous of cost function, right? But there's no such requirement in the reward function. It can be discontinuous, it can be whatever you want. It can simply be if statements, and it'll still work. Clear? So now you know what model-free reinforcement learning is, why and how it is different from classical controls, okay? Now we'll go back to model-based reinforcement learning. In this one, what you try to do is, you try to learn the model, okay, first, and then develop a strategy for that, okay? And by learning the model here again, you don't mean exact physical, understanding the physics of the model, okay? You simply understand the input-output relation, you learn that input-output relation, Based on that, you will develop the controller that you have. Okay. Now, why do we even need this? Because in theory, this is more sample efficient. Okay. In the sense, when you're developing a controller itself, you try a lot of different scenarios. However, when you're just trying to understand the input-output relation, you require far less number of samples, which would in turn result in a more efficient process. Clear? Clear up until this point, yes?
Learning the model is an RL task, or it's like basic system identification methods?
Yes, it is system identification methods. So, but here the system identification, okay, classical system identification method, what you do is you have a known structure of the system, like say maybe a transfer function, yes, say you have ts square plus 1 times ts plus k, right? So you define a structure first and you then try to find, try to find the parameters, okay? Here, you don't even have to define the structure, okay? You don't have to define that structure. Clear? Clear up until this point, everyone? Yes?
Here you mean like model free,
right? No. We are learning the model, but structure free rather. This kind of structures that we define in classical control for system identification, we don't have to do that in model-based reinforcement learning. Because what we do is, okay, assume the UAV scenario. What we do is, we map basically the thrust inputs that we are giving to the output. As in, say you have a quad rotor. You have 4 rotors, okay? M1, M2, M3, M4, okay? Say the RPMs are 1700, 1750, 1700, 1725. For this set of RPMs, your UAV is hovering, stable hovering, okay? It's exactly hovering as it, very stably, okay? For this set of RPMs. You try that for again different set of RPMs to understand at what RPMs will it roll, what RPM it will pitch, what RPM it will yaw. All you do is you get a huge table of, well, not exactly very huge, but then you get a samples for this thing where you have this input, this is your input basically, and then this is your output. So you get a table of input and output. So for input 1, say this is I1, your output is O1.
like a lookup table, like we use.
Exactly,
That is
exactly.
model-based, right?
That is how the system learns the model basically.
But yeah, so that is considered model-based as
Yes.
opposed to model-free. So model-free, going back to this earlier question, so when we do system identification, that is considered model-free?
No, in model free, you don't have to care about the system. You don't do system identification. System identification is done in model-based reinforcement learning. System identification without a known structure. Is that clear? Okay. Okay. Now say,
How come without a known structure? Like
you don't have to define such a structure.
when we do system identification, we don't have such a structure?
No, you don't. I mean, in model-based reinforcement learning, classical system identification, yes, you need these kind of structures, right? In model-based reinforcement learning, what it will do is it will basically learn a black box which will map inputs to outputs. So you will learn this black box, which in most cases might be a neural network. So you learn a neural network, or rather you train a neural network which would give you certain outputs for given inputs. Example, I'm thinking of some example. Okay. This black box doesn't have physical equations, as in here, as in classical system identification. Now we are not talking about model free. Model free is completely different. Now we're just talking about model-based reinforcement learning. So generally the purpose of RL for control is to train an agent that can learn the control policy. This is what RL for control does. Okay. However, with model-based reinforcement learning, what you do is RL will first perform system identification, and based on this, it will learn a control policy. There's basically one additional step in model-based reinforcement learning as opposed to model-free reinforcement learning.
When we have a plant, for instance, with model free,
Mm-hmm.
and we just use it to experiment with the policies until we learn the
Exactly, exactly. So if you already have a black box, you can use model-free reinforcement learning. That black box can be either known physical equations from first principle methods, or it could be a physical system, it could be anything. However, in model-based reinforcement learning, we first identify the system or learn the system, but not in the sense of classical system identification where you have to define the structure. You don't have to do that. You just learn a black box, which you name it as the system itself. Yes?
Is it necessary to have a physical system to really that?
No, no, not required again. So if you have a reliable virtual replica of the physical system, it would still be the same system, assuming that the virtual replica is exact model of the physical system that you have, right? Now there's a reason for doing the system identification, for learning the model, okay? And that is, once you learn the model, okay, when you are using model-free reinforcement learning, it is basically very task specific. It's not task agnostic, in the sense that RL agent that you develop for a given plant and a given task, as in UAV hovering, okay, that will have a certain policy. And your RL agent will learn exactly that policy for that given system. However, so now you say you want to do a trajectory tracking problem, which moves in 2D, okay? Your RL policy that was trained using this model-free reinforcement learning will not be able to do this trajectory tracking problem. Why? Because it learned the exact policy, it learned the exact inputs to give to that system to achieve the already defined task. However, with model-based reinforcement learning, since you learned the model here and you have identified the system, it is slightly more easier to change the task because you already have the black box of the system. So the same UAV that hovers can also move along 2D axis, right? And in this case, you simply have to skip the first part and you start from stage 2, where you are learning only the task and not the plant itself.
So more task agnostic, right?
Yes, more task agnostic, exactly. Okay? Yes, this is exactly that what we talked about. So MBRL will first observe in the sense that it will try to generate this table. I'm stating table here because assuming that there are only infinite number of combinations. However, for most practical cases, you might have infinite combinations of this and you cannot use a simple table there. You will end up with a neural network maybe, right? So you observe, then based on that observation, you learn the model. Using that learned model, you plan, and then you act in that model. You keep repeating that basically till you learn the task that you want to learn. Clear? Sure. Yes.
A point, the model-based RL. We said that model-free is like more of a task dependent.
Yes.
This means when I did a model-based RL,
Mm-hmm.
I have a part of the learning as the model, then I'm working on the task,
Yes.
or the algorithm can work on.
Theoretically, it will work in one go. Like it will first, but internally, it will first learn the model, and then it will learn the task that whatever you have assigned it to.
So I can take this model and like use it any
Yes,
other.
yes. You should be able to do it. Yes, that depends on the algorithm. The MBRL algorithm that you're using. We'll be going over very briefly about a few MBRL algorithms. So you will see how they learn the model, right? So based on that, it will be possible or not possible, or rather feasible or not feasible to extract the learned model, right? So, generally, any MBRL algorithm works like this, like just as we talked about, right? Initialize a policy. Basically, policy is what? Set of actions. So it will start with some random set of actions. It will bombard the system with that set of actions, get the outputs, try to map this input and output in some way, which it would then label it as the system, and then based on that system, it will try to learn the policy or the task, learn a policy for the task that you want to do. Yes?
So like you conclude that model-based is either it would be a lookup table or
Neural network.
deep learning.
Yes.
So that being said,
Mm-hmm.
then anything that we did where we developed a lookup table, like
Right.
like when we did policy iteration, right?
Okay.
That is considered model-based.
Okay.
right?
No, here the lookup table is just for the system dynamics, not for the task. Right? There you don't care about the intermediate system learning. There you are just like this input will give you this output. Here what it does is, say even if your task is 2D motion, okay? But this will still learn or still at least have data for hovering, what values you need for hovering. Right? That is what model-based reinforcement learning will do. However, model-free or the tables that we had earlier, the Q-learning tables, that doesn't do that. All it does is, in this state, take this action for that system to complete that task. Here, it is, in that state, take this action, you will get this output, that's it. Irrespective of if whether that task or that action will help you complete the task or not.
So are you trying to say that the lookup table is not really, like is
It's just for the
model,
system.
define the model.
It's just for the
the
system
system,
model.
yeah.
Yes, it's just for the system model, not for the task.
Not like we used to do where we had action and
Yes, not like that, not like that.
Right?
That's why if you remember, that table had states and actions. However, this one has input and output. Right? So what exactly, now this I think will make it more clear. By learning a model, we mean learning a predictive model that will help us understand what action will lead to what state, irrespective of the value of that state, as opposed to Q-learning where we learned the value of taking a certain action in a given state, right? You get the distinction here, right? 100% clear? 100% clear. Should I include this in the midterm? You'll have more questions then. Okay. So yes, you collect experiences by taking actions in that environment, okay? And then use that learned model to generate a policy, like I said. So there are two steps. This system identification or learning the model, then you use that to to generate your policy. Cool? Okay. There are different algorithms. One of the most common model-based reinforcement algorithm is called DINA. Okay. So here in this one, this is the classic MBRL algorithm. So what you do is you first learn the model by generating a lot of data on the real world system, and by real world here it could even mean simulation, okay? Not exactly the hardware plant, but a representation of that hardware plant, either in real world or in simulation or in the virtual world, okay? Any of that will work. Then the agent interacts, okay? Again, this tuple, you remember, this is very important in reinforcement learning. State, action, rewards, next state, okay? You generate a table of that, and then, then that model is used to learn or generate the policy. Cool?
So that table is considered my model?
No. Based on that table, we extract the model. That table again will this table, you will have to define some equations, if I may say. Neural networks are also equations but more non-linear, which will map given inputs to outputs. So if you have any system or any method to map the inputs to outputs, that is your system.
So in other words, like your SARS prime will train your
neural network to learn the model. Yes. Okay. Now, learning a deterministic model will in some sort defeat the purpose of reinforcement learning, right? Because you want it to be more adaptable, more versatile than classical controls, right? Then for that you have this algorithm called PETS, which is probabilistic ensemble with trajectory sampling, okay? So what it does is you have multiple neural networks now, okay, working simultaneously to identify the systems, right? And then when you give action to one neural network, you give the same action to multiple neural networks and you see what output you're getting, right? And based on that, you weigh them together, basically, a weighted average. And that weighted average would be your system. This will help us account for uncertainties in the system, right? A very crude explanation of what PETS is.
This prediction will be learning being supervised or unsupervised?
Okay. It will be supervised in the sense, self-supervised, I would rather say, okay? Because you are not giving it the input and outputs. The agent itself or the computer itself will generate that input-output. If you are giving it, then it's simply supervised learning, right? So the computer or the agent itself will do the data collection part for you. Supervised learning is what? Data collection, first step, or labeled data collection that you have, plus training itself, right? Training. This would be supervised learning, right? You're doing only this because your RL agent will do this by itself. You get it? Label data, oh sorry, this is, the training part is supervised learning. However, if this part is also done by the computer, then it is self-supervised learning, right? Because you are not providing the data. No labels, nothing. Either unlabeled data, as in case of unsupervised learning, or supervised learning where you provide labeled data. You're not doing either of that, okay? You're simply giving it the system and you're on your own now. Generate actions, whatever you want to do, train yourself. That's what you're doing there, okay? Yeah, this I will upload anyways. This is again just a different version of PETS, so I'll not go in detail. This is an interesting one, okay? Remember I told you that reinforcement learning is multimodal, right? In the sense that you can have image-based input and you can have numerical outputs, right? Numerical values as your outputs. Say you have the image of the scene where your robot is, and your output could simply be the velocity of the joints of that robot, right? Now images are difficult to process with, okay? How many of you are familiar with convolution neural networks here? Okay. So in the paradigm of computer vision, you have something called CNNs, okay? CNNs help us work with images, right? So you have images, you have CNNs, okay? The normal neural networks that you have are usually called ANNs, artificial neural networks. There you just have neurons. Neurons piled up together in different layers and different numbers in each layers, and in between you have activation functions. CNNs differ in the sense that they have something called filters, and then they have convolution layers, right? That is what gives the name convolution neural networks. Basically, to sum it up, convolution neural networks help you work with images, okay? But they are very expensive and computationally demanding to work with such systems, right? So what generally is done, no, not generally, what is done at times in computer vision paradigm is to take an image that you have, okay? An image can be a big image, right? Every pixel have a lot of information, right? But usually the information that is of use that you want, the information of interest is very small in that entire image, right? You don't want the entire image to be processed because you have to do it. CNN will process every pixel of that image, which would be computationally demanding and expensive, which would in turn slow the process. You don't want to do that, okay? So there is a kind of paradigm again here where you have, it's called autoencoder decoder, okay? Where you take in an image, okay? You compress that image in a latent space where you basically end up having very little information but the useful information, okay? And then you work with this. This is a latent space denoted as Z usually. So you use this latent image or latent space information for whatever processing you want. After doing the processing, again you push it into the decoder, which will then recreate whatever output you want in the form of, say, image again, okay? This kind of model-based reinforcement learning
Just
yes?
is that encoder decoder or
Encoder decoder. Encoder decoder. So yes, because
you misspoke. That's all.
oh sorry, okay, yes. You have encoder decoder. So what you are trying to do here is, in model-based reinforcement learning is, say you're working with images, okay? learning an entire image will be difficult, very difficult, right? So what you do is when you get the image, you simply squeeze it into the latent space. Based on that latent space, you do the processing, that is learning the policy, ideal policy that you want, and then when you get the learned policy, you push it again through the decoder. Okay? That's why it's called dreamer, because it's assumed here that the RL agent will dream the policy, right? Yes.
I just have a clarification because you mentioned about CNNs that they boil down to the difference here is the filters and the
Convolution layers.
So the convolution layers, like going back to the encoding part, is that where you squeeze that out of them embeddings that are
Or useful.
yeah
Yes.
and lower and damage and thus it's computationally more effective.
You mean the principle of encoders, right?
No, I mean like the in the case of CNNs, the convolution layer. Is that what it does? Is that you get out of them the embeddings, so you don't have to really deal with the whole.
Oh yes. So that way you end up with a very compressed information. Images are nothing but numbers in huge numbers, right? Like as in matrices of numbers, right? Huge matrices of numbers. So you simply want to compress that information. When you get the latent information, the latent space representation rather of that input, whatever you have, you use that to process your RL thing here. In this case, the generation of the policy, learning the model plus generation of the policy. So it's done in the latent space. Everything is done in the latent space. And this latent space basically is like a dream here, okay? Because it's not the real thing that you have. You're simply working in a compressed form, in a compressed world.
One last question.
Yes.
So over here, the encoding part is like is the convolution layer, or is the embeddings from the convolution layer being fed into the encoder?
Again, sorry.
The encoder here.
Uh-huh.
Like when you explain things, is it the convolution layer, or is the convolution layer precedes?
No, this will be just a vector. This will not be a convolution layer. The latent space will.
Where is the convolution layer here?
It will be here, right here. It will be again.
So your encoder is basically the where convolution takes
Yes, yes. It will be filters and convolution layers of diminishing sizes. That way you compress the information as you go as you progress in the number of layers that you have. The information keeps getting compressed because of the filter sizes that you have. Okay? Clear? Okay. Yeah, so this is the model. It has different, this is the working principle. I want to skip it because I want to go to the next topic. Again, different kinds of reinforcement, model-based reinforcement learning algorithms where you learn the model in different ways, right? In the sense that you don't learn the exact deterministic transitions, rather you learn more of Gaussian processes, right? So now your input could result anywhere on this curve maybe. Your input could result, the output could result anywhere on this curve rather than a one-on-one mapping, right? This would help you account for uncertainties. And in few, I'm summing up all the model-based reinforcement learning algorithms here. So in few algorithms, what you do is you limit the number of steps you move forward to reduce the uncertainty, or you somehow account for the uncertainty in the sense of penalizing it maybe. That okay, fine, the more uncertain outputs you have, the lesser reward you get. That way you learn a more precise, or rather more close to real world representation model, right?